Miss Liam's chemistry class. Here is your puzzler. And in case you forgot what I look like, here's a picture of me from Halloween last year. I am dressed as a cation, and we're going to be talking about some cations today. So your homework this week is to turn in these notes and to write up your rock candy lab and fill out a Google form. All right, here we go. So acids taste sour. So for example, lemon and vinegar are acids. Acids produce hydrogen ions, so H+, in solution. If you have a strong acid, that will completely split apart in water. So the two ions that it's made of will split up into solution and be completely separate from each other. So the hydrogen ion is the piece that will react with other chemicals. Weak acids only partially split apart in water. So if you have something like nitrous acid, then only some of this molecule, it's not a molecule, this compound will split up to make hydrogen and nitrite. Some of those hydrogen and nitrites will come back together to go backwards and form that HNO2 again. So that's what this arrow stands for. It is the equilibrium symbol. It means that the reaction can go both forward and backwards. It does not mean that there is an equal amount of each of the chemicals. It just means that the reaction can go both forward and reverse. We'll talk more about that in the coming weeks. Some examples of acid include hydrochloric acid, phosphoric acid, sulfuric acid, nitrous acid. I didn't ask you to name these earlier, but you would want some practice on this. Okay, so hydrochloric acid is from chloride. So if the anion ends in "ide," we use the prefix hydro and change the ending to "ic acid." Phosphoric acid is from phosphate. So the ATE ending goes with the "ic acid" ending. There's the phosphoric acid. The phosphate is PO4-3, so that's why we needed 3 of these hydrogen ions. Sulfuric acid is H2SO4, same naming role as the phosphoric acid. And the nitrous acid is from nitrite. So we can see these different endings on the anions will give us different endings on the acid names. So please fill out the following chart, and you can definitely use the internet if you like. See if you can figure out the patterns. All right, so the bases. Bases taste soapy, but you don't want to taste either acids or bases unless it's like an actual food item. Bases will produce hydroxide ions in solution. Strong bases will completely split apart in water. So for example, sodium hydroxide is a very typical base. We can see that the sodium hydroxide is a solid here, and it's splitting up to form 2 aqueous ions. There's actually a heat of solution for this. Oh, it's in the wrong spot, sorry. It's a highly exothermic reaction, so it's negative 44.5 kilojoules per mole is the heat of solution. So heat is actually released when this ion dissolves. All right, so please write the chemical formulas for these bases. Pause the video and do that. If you did the calcium hydroxide right, you should have gotten that formula. Just a reminder that the ion charges have to balance out. So the calcium's in the second column of the periodic table, so it's +2. So we're going to need 2 of the hydroxides to balance it out. Now water itself will actually split up a tiny, tiny bit all by itself. So it's almost like a very, very, very weak acid and very, very weak base. That's called the autoionization of water. So there's the equation for it. We can see that equilibrium symbol there. So some of it will split up, and these ions will come right back together to form water. Another way to show this is with 2 separate water molecules. The hydrogen ion, instead of being floating around by itself here, it actually attaches to another water molecule, and we end up with H3O+ and hydroxide ion. This piece of it, the H3O+, is called hydronium. Either one of these formulas is correct. I just want to have a little side rant, if you don't mind. There's a type of facial product line called H2O+, but this has always irritated me because there's no such thing as H2O plus in chemistry. It's H3O plus, and their logo is wrong. You can see that there's the lowercase h here. So I've never bought this product. There's chemists that work there, but that's funny to me that the formula is wrong and they name their company after it. That said, if anyone wants to buy me some of this or give me a free sample, I'm going to use it. It's free, you know. Okay, at any rate, when the water splits up, it's only going to form a very low concentration of the hydrogen ions, so 1 × 10⁻⁷ molar. So that's a very, very small concentration. That's what these brackets mean, by the way, is the molarity. It's a shortcut for saying molarity. So you can see that these numbers are pretty messy. So a different way of showing a hydrogen ion concentration is by using pH and pOH. You, I'm sure, have heard these terms before in other classes. To find the pH, you take the negative log of the hydrogen ion concentration, and that will give you the pH. Okay, pOH is similar. When you add the pH and the pOH of a solution, you end up with 14. That goes back to the fact that water auto-ionizes, and you can see the 7 over here and the 7 over there. When you take the pH and the pOH, you end up with 14 altogether. So if you want some more information about logs, log functions, you can take a look at this optional video. Some of you have already studied logs, but you don't need to know really what they do. I hate saying that, but you know, you can find a pH without understanding what a log function is, but it's helpful if you do. Okay, here's a little scale of different types of solutions and their pH. I edited this a little bit because a car battery is acidic. It has sulfuric acid in it, but the picture they had earlier was of like a AA battery, and those are alkaline usually. So anyway, so I updated this a little bit, but you can see the various pH levels for various everyday items. Most of the foods there are acidic. The water is right in the middle at 7, so 7 is neutral. A pH above 7 is considered basic, also known as alkaline. pH below 7 is acidic. Now, if you can't remember which one is which, I found a little thing for help you remember. So if someone says they're a 10, you could say, you're a 10, maybe on a pH scale, because you're basic. Get it? Okay, well, give it a think if you don't get it. All right, so here's some sample calculations for you. Calculate the pH with a hydrogen ion concentration, 1 × 10⁻�3. We plug this into the pH formula, and you should get 3. So take a calculator, make sure you know where the buttons are to calculate this. Okay, for the second part here, for the pOH, we don't have the hydroxide concentration, so we can't use this formula, but we can use this formula. You just plug in the pH here and solve for the pOH, and you get 11. So as always, make sure you know how to do this and you're not just writing down my answers. Use a calculator. All right, the backwards of a log function is this. So the log functions we're using back here, by the way, are log base 10. So you just take 10 to the negative pH, and that pops out the hydrogen ion concentration again. Okay, so if we want to find the hydroxide concentration from earlier, we're going to use this middle formula. You plug in the pOH right there, and you get 1 × 10 to the negative 11 molar hydroxide concentration. Really small amount, negligible, you could say. You can't really measure that, it's so low. Okay, now the next few bits are, I'd like you to read this article about pH and how that affects your teeth. Just kind of connect that back to why we even care about pH. It is really important, by the way. Okay, lastly, you're going to balance some chemical equations. When we add an acid to a base, we end up with an ionic salt and water. Okay, just to note, it's not always a 1-to-1 ratio. So again, it's a double replacement, so we have H going with OH and the Na going with the Cl. Now in this case, it is a 1-to-1 ratio. The Na is a +1 charge, the Cl is a -1 charge, so those get together to form NaCl and H2O. So instead of writing HOH, we rearrange that to make H2O. For the second equation, I'd like you to pause the video and give that a try. Now this one's a little more complicated because the phosphate has a -3 charge. So the two compounds you should have gotten were Na3PO4 and H2O. I'm going to balance those by putting some coefficients in. You have a few more of these to try. Try not to look them up on the internet and try to really balance these. I gave you some hints here on the first one. I gave you some coefficients. All right, and finally here is the puzzler answer. It's either order online or online order. And just for making it through this whole video, here are a few extra puzzlers for you to try. Good luck with that. And if you have any questions about any of the notes or the other homework, please see me during the Zoom meeting. Bye.